Hello everyone, welcome to module 3 of the Essentials of Turbulence class. In this module, we are going to deal with the equations of fluid motion. Here are the contents. We'll talk about the nature of turbulent flows. We'll deal with the continuity equation, the momentum equation. We'll talk about pressure and the role of conserved scalars. Then we will discuss the vorticity equation a little bit and delve into rates of strain and rotation. We'll look at some transformation properties, discuss the Reynolds number similarity, and discuss further a property called invariance a little bit. Okay, so here this is the source that we have been using for this particular module. We start by discussing the nature of turbulent flows. So as you know, we have discussed this at length, right? How turbulent flows are different from laminar flow. There is irregularity. There is it exhibits a seemingly random behavior, right? When we say random, now we have to say it looks random to us, although it is not random. So that chaotic nature will be there. Right? That irregularity will be there. And that's one of the main features of turbulent flows. That's how you can immediately distinguish it from a laminar flow. So what is shown here on this slide is the velocity recording in a turbulent jet experiment. It is the time history of the axial component of on the center line of a turbulent jet. So this is what I have, right? I mean, if I have some kind of a nozzle and through that, and let's say it has a diameter d, then the turbulent jet will look like this. If it is a turbulent jet, it won't have well-defined edges. It will be irregular, it will be slightly chaotic, and so on. And we consider this to be the axial direction to be 1, the transverse direction to be 2. So that is the transverse or the radial direction. Assuming this is a round jet, we are talking about R, we are talking about X, R, and theta. Those are the directions, right? So this is the direction X or 1, and the radial direction is R or 2, and the azimuthal direction is theta or 3. Got it? So what is shown here is u1t, the axial component of the velocity. So the subscript 1 represents the fact that it is an axial component of velocity, and it is the time history on a center line of the jet. So this is the center line. This is the center line. On the center line of the jet, this is the time history at a certain point. This is from the experiments of Tong and Warhaft in 1995. So now you can see that there are a lot of fluctuations in the velocity recording. There's a line here which is the mean, which represents the mean of this signal, the mean of this velocity. So you have u, which is a vector, and it is a function of x, the position vector, again a vector, and comma t. So it is a 4D variable. The velocity vector is a 4D variable. Now this has multiple components, correct? So this will have u1, u2, and u3. u1, u2, u3 are scalars. U is a vector. Now this is an instantaneous variable. It depends on time. It's an instantaneous variable. And you have your u1, u2, u3, again instantaneous. Those are also 4D. So u1 is u1 of x as a vector, comma time, because it also depends on space and time. So what is shown here is u1 at a particular point along the center line. So that is the recording that is shown here, and the mean of that value is what is shown in this line. I hope this is clear. So our fluid velocity as such is a 4D variable, is a 4-dimensional variable, x1, x2, x3, and then time. The position vector x is x1, x2, x3. Now, coming back to the behavior of u1 of t, it clearly is irregular. There are a lot of fluctuations. And it is expected that it is going to behave irregularly with position and time. What is shown here is a time history, and the mean is taken. Now, as a general observation, we can say that the u1t displays a lot of fluctuations, sometimes more than about 25% about the mean, and the mean is represented by this angle bracket. So u1 mean. So that is the mean velocity. The mean velocity is going to stay steady. That's going to be a constant. That's not going to change. In this case, that's about 3 point something. But as you can see, the velocity fluctuates between 1 point something to 5 point something. So that is the amount of fluctuations you're having. So about 25% fluctuations are there. So this is from a real experiment. Now, what I'm showing next is the mean velocity, mean axial velocity, again on a turbulent jet. It's from a different turbulent jet, not from Tong and Warhav's experiments. It's from a different turbulent jet. Nonetheless, it is a turbulent jet. The mean velocity here is normalized by its centerline value. So it's a normalized value that is shown here. This is the mean velocity. U1 is the mean. And u1 with a subscript 0 is the value or the mean on the center line. This is plotted against the cross-stream coordinate, as in the radial coordinate. I had showed you what the radial coordinate is here. X, R, and theta for a round jet. So that radial coordinate is also normalized with the distance from the nozzle. So x2 over x1 is what is shown here on the x-axis. And the normalized velocity is shown here. So this is the mean. This is for a Reynolds number that is 95,500. So very high. So clearly this velocity, this behavior seems like very stable. It's smooth. So in that sense, both are stable, because if I go back and look at this velocity, the instantaneous velocity, yes, it is exhibiting fluctuations, but I don't have really wild fluctuations sometimes. I have fluctuations that stay of the same order of magnitude over this period of time. So I have a fluctuation here, here, going to this level, but not like something really wild. So in that sense, it is kind of stable, right? It's not going out of proportion. It's staying within the same order of magnitude, meaning it's staying between 1 and 5. Reasonable time to make the recording, it is staying between 1 and 5. It's not going to 100, for example, or 50 even, right? It's staying in the same order of magnitude. The mean of U1 is definitely stable because it seems very smooth, no irregularity, right? So we don't see huge variations in U1 of t, the instantaneous, and so we are saying it is stable. And U1 mean is also definitely stable because it has a smooth behavior. Another couple of points I want to point out where with regard to the instantaneous velocity, it is definitely not periodic, and we didn't expect turbulence to be periodic. And it does exhibit wide range of time scales, right? Some fluctuations are very short and some are here like this. So clearly there is a wide range of time scales. And even if it fluctuates, it doesn't stay there for long periods of time. So for instance, you don't have something that looks like this. You don't have something like that. It is fluctuating, but it's immediately coming closer to the mean and staying closer to the mean. Then it goes down a little bit, then goes up again. It's not spending a long period of time above its mean. So that's another observation that I wanted to make. So this is the nature, right? The irregular nature. And we are seeing that through a real velocity measurement in a turbulent jet. So as I was saying earlier, the U1 mean definitely has a smooth profile. No fine structure, no different time scales. It's all like one smooth profile. And you would tend to think that the mean actually looks like a laminar profile, but that's not the case. You would, if you go back and look at the laminar axial velocity in a laminar flow, it'll be different from what you're seeing here. So this irregular nature is obviously what allows turbulence to mix things faster, to transport things faster. So the enhanced diffusion, like we have discussed it a lot. And that was clear in Osborne-Reynolds experiment as well. This is also something that we have discussed. So this ability of turbulent flow to transport and mix fluid much faster than a laminar flow has a lot of different applications in engineering, right? And in nature as well. And we have discussed all of that. So that takes us to the equations. Now, we know that the Navier-Stokes equations are going to represent the turbulent flow. So now let's look at the equations in detail. And before going over the equations, one thing that we will definitely have to cover is the continuum hypothesis, because we have to make sure that that is understood, right? The continuum hypothesis has to be valid, otherwise the equations are not valid. So that means the average spacing between the molecules, or the mean free path, the distance that one molecule has to travel before colliding with another molecule, that is the mean free path. The mean free path typically is approximately 10 to the negative 9 meters for air at atmospheric conditions. Now at extreme conditions that could change, but we are talking about standard conditions. And air is now for liquids this will be slightly different, but let's just consider air and compare that to the geometric length scale of the flow. What is the smallest length scale that you could probably imagine? If you take a turbulent jet, definitely not more than 0.1 mm. So that's about 10 to the negative 4 meters. So look at the separation between the mean free path and the actual length scale. So we are talking about lambda over L, which is what the Knudsen number is. And if you take that Knudsen number, lambda over L, in this particular example is already 10 to the negative 5. It's a very, very small number. So for the continuum hypothesis to be valid, Knudsen number has to be much less than 1. So that is first. Let's keep that aside because you have to make sure the continuum hypothesis is valid before you even discuss the Navier-Stokes equations. Okay. Now a couple of other terminologies or contexts that I want to present here is the Eulerian versus the Lagrangian. Now what does Eulerian mean? Eulerian means you have the observer is fixed and you are looking at flow past the observer. So you are fixed at a point and you are looking at the velocity, temperature, density of the fluid at that point. On the other hand, versus a Lagrangian description would be you're following the fluid. You're following a fluid particle and you're recording the velocity, density, pressure of that particular fluid particle as it is moving along. So the representation notation is we have rho comma u. Rho is a scalar, the density it's a scalar, but it's still a function, it's still a 4D variable. In a realistic flow, it's still a 4D variable because it depends on the position vector x, x1, x2, x3 and time. And then you have the velocity vector u, that's why it's in bold, function of position vector and time. That's an Eulerian representation. A Lagrangian representation, what we would do is we use the superscript plus to indicate that it's a Lagrangian description. So the Lagrangian feels x plus, okay, which is a function of t comma y, where that represents the position of the fluid particle. If x plus represents the position of the fluid particle, and we are calling that y, and again it will be in bold because it is a vector. It has 3 components. That will indicate the position of the fluid particle, and then you would have rho plus, which is the density of the fluid particle, which is again a function of t comma y because it is a function of the position, and u plus, which is the velocity of the fluid particle, which will again be a function of time and the position as well. So t comma y. I hope that is clear. Eulerian versus Lagrangian. The other concept that we should also discuss is the material derivative, also called the substantial derivative. We represent it mathematically by writing it as capital D dt. So d dt is del del t plus u dot del. A material derivative is also called a total derivative. This term right here is a local term. It's an unsteady term, local term. This is like a transport term, also called convective derivative. So local derivative, convective derivative. So you have total derivative is local derivative plus convective derivative. So those two things. One more point that I want to make here is related to the material point. So material point is a fluid particle itself, which is defined by its position y, again be a vector because it has 3 components, at time t0 of course because the position is changing, and by its movement with the local fluid velocity. So if you have a material point, you have material lines, you have material surfaces, and you have material volumes. So all of these are defined similarly. Material point is a fluid particle, material line is a locus of all the fluid particles, and material surface is something, a surface that is obtained by sweeping a material line, and material volume is a volume that is obtained by sweeping a material surface. All are defined similarly. So if you have a material surface S of t, it is defined by the property that at every point of S of t, it moves with a local fluid velocity, the fluid velocity of that particular material point. And across any material surface, there is no mass flux. So those are the 3 things that I wanted to cover before I start with the equations. Now let's go into the equations, starting with the conservation of mass or continuity equation as we call it. It is del rho del t plus del dot rho u is equal to 0. Rho is the density, u is the velocity vector. This is the divergence operator, isn't it? Rho is a scalar, u is a velocity vector, t is time. So you have the unsteady term plus a divergence term is equal to 0. Another way to write the continuity equation is as follows. The way you get this is, you can write this as del rho del t. The second term, the divergence term, you can use vector identities to write it as rho del dot u, okay, plus u dot del rho, u dot del rho. Now what I can do is I can combine these two and use the definition of the material derivative. Then I get d rho dt plus rho del dot u is equal to 0. I divide by rho, and what I have is 1 over rho d rho dt plus del dot u is equal to 0. I can write this in, so this is another way of writing the continuity equation. 1 over rho del rho del t, 1 over rho d rho dt plus del dot u is equal to 0. Now, if I use the definition of the specific volume is 1 over rho. remember this is specific volume, is 1 over rho. I can substitute that into this equation, and then what I'll get is V d of 1 over V dt plus del dot u is equal to 0. And then what I'll have is, I can write this as minus 1 over V dV dt plus del dot u is equal to 0. How did I get that? Because I have d1 over v, which is minus 1 over v squared. So I have a v on the numerator becomes minus 1 over v, and then this is essentially minus d dt of ln v plus del dot u is equal to 0, which gives me d dt of ln v, specific volume, is equal to del dot u, which is what equation 2 is. So the two boxed equations are two additional forms of the continuity equation. The main form is what is shown here. Del rho del t is del dot rho u. Now, if the flow is incompressible, then rho is a constant, in which case all you're going to get is the velocity being divergence free. So you're going to get del dot u is equal to 0. Or it is solenoidal as we call it. So the velocity is divergence free, and so del dot u is equal to 0. So that is the continuity equation. Now let's deal with the momentum equation. The momentum equation comes from the first principle, that rate of change of momentum. So Newton's second law, isn't it? Newton's second law. Rate of change of momentum. So I'm going to call it dp dt, or I should actually call it its total rate of change of linear momentum. So it is dp dt, where p is the momentum, is rate of change of momentum is sum of all forces. That forces include surface forces and body forces. So essentially it is Fs plus Fb, surface forces and body forces. Now, the rate of change of momentum can be written as rate of change of velocity. Mass is a constant because momentum is just mass times velocity. So eventually what you get is du dt is the force, sum of all forces per unit mass. Now, the surface forces are of molecular origin. What do I mean by that? Surface forces are coming from friction, viscosity, so of molecular origin. Body forces, example would be gravity. For the purpose of this class, we can just neglect gravity and look at the rest of the terms. And that's what we'll do. So we will only look at the surface forces here for now. In that case, your momentum equation is this one. Rho duj dt is del xi tau ij. Tau being the symmetric stress tensor. The left hand side is essentially the rate of change of momentum. And the right hand side is the sum of all forces. Mainly we are only considering the surface forces for now. So that is written in terms of the stress tensor del xi tau ij. You can, for Newtonian fluids, which is what we are going to consider in this class, for Newtonian fluids, you can split the stress term into a isotropic deviatoric part, into an isotropic part and a deviatoric part. Isotropic means it is independent of direction of rotation. It is independent of rotation. So you are writing this, so the pressure is the isotropic part. It doesn't matter which direction it is. Pressure is a scalar, right? So you just have pressure at a point. It doesn't matter which direction it is. So that's why you're writing it as minus P delta Ij. Delta Ij, remember, is the Kronecker delta. So I have tau ij is minus p delta ij plus mu, which is the viscosity, absolute viscosity or dynamic viscosity, times del ui del xj plus del uj del xi. So that is your stress tensor expressed as a isotropic and a deviatoric part. So that is your stress tensor. So what we have looked at here is the continuity equation and the momentum equation. The continuity equation, we wrote it as del rho del t plus del dot rho u is equal to 0. You have an unsteady term. And then we represented it in two different forms. One as a material derivative of density and another as a material derivative of specific volume. Remember, specific volume is inverse of density. Then we looked at the momentum equation. Momentum equation coming from Newton's second law is represented by this equation here. Rho duj dt, capital D is material derivative, okay, is equal to del tau ij over del xi. So then you represent the stress tensor as an isotropic part and a deviatoric part. And then we'll put this together into the momentum equation in the next class. Thank you.